All right. Yeah. Thanks to the organizers for the invitation, for everyone for coming. So I want to start about 5 years ago when SrOH was first laser cooled. This was the first demonstration of laser cooling of a polyatomic molecule. And the thing that I think I find most interesting about this paper is not necessarily the really beautiful results of laser cooling working very well, but the introduction, which describes the point of laser cooling molecules as opportunities for advancing fundamental physics, chemistry, and quantum technologies. And this is really pretty vague. The actual specific applications of these molecules were not really worked out. And I think the thinking at the time was you do this, put the idea out there, and then people will start coming up with more things to specifically do to advance all of these directions. And so I want to tell you about 2 applications that we're working toward in SrOH specifically, rather than just polyatomic molecules generally. So first is an ultralight dark matter probe. And the mechanism that we're exploiting in polyatomic molecules here is that polyatomic molecules have multiple different vibrational states. So here we have a ladder of bending mode vibrations and a ladder of SrO stretching vibrations. There's also an OH stretch, which doesn't come into the physics here. And in any molecule where you have these independent ladders, if you climb high enough in the ladders, you're going to eventually run into an accidental near degeneracy. It happens that in SrOH, this near degeneracy occurs pretty low down. So this 200 state, if you try to laser cool and trap it, will just get populated through your optical cycling. You don't even have to work to populate this state. And these near degeneracies can be leveraged in fundamental physics searches. And in particular, if you probe the resonance between these vibrational states and keep probing them over time, you can be sensitive to certain dark matter models. The way this works is that each state independently is sensitive to the proton to electron mass ratio, because vibration energies in molecules generally are sensitive to the proton to electron mass ratio. And the dependence of the harmonic and anharmonic contributions is different. The bending mode is more anharmonic than the stretching mode. And so if the proton to electron mass ratio is oscillating in time, then the resonance between these will oscillate. And certain kinds of dark matter will couple to the proton to electron mass ratio, and the dark matter field itself will oscillate in certain models, and that induces an oscillation of this resonance. So the degeneracy comes in just because it's very convenient and has some favorable systematics properties to measure these kinds of very small changes in the resonance using microwaves. That's not conceptually necessary, actually, and there's some very interesting proposals, especially I'll point out a proposal by Mike Tarbet to measure the corresponding splitting between 0, 0 and 1. The second 2 numbers don't exist in CAF. Using Raman transition, this is also sensitive to the same physics, but that's not a microwave transition. So we're interested in this because we think that it may have some promising systematics properties and just be easier to do with microwaves. So that's the last I'll talk about this sort of specific physics. And I also want to motivate working with SrOH in terms of poly-EDM, which Nick talked about. And just to review the idea, this is a figure from the original proposal paper, which shows YBOH in the bending mode. So YBOH in its ground state is linear, but in the bending mode, it looks bent. And these polyatomic molecules are really promising for EDMs because you can polarize them in low fields. With this optical cycling center, you can laser cool and trap them. You can reverse their orientation in a fixed external field. And something I want to focus on here is that the choice of both the metal and the ligand is very flexible. This is a pretty broad class of molecules you can choose to work with. So you can work with these linear molecules or a symmetric top or asymmetric tops. And I want to focus on why we're interested now in working with a strontium as this metal. So a figure of merit for the cycling center, you take the intrinsic sensitivity, which tends to grow with larger metal mass, you can plug in some numbers which I think are reasonable starting points. Of course, you have to see what you get in the experiment. And then you can project how many you would have to trap per iteration of your experiment to match the Acme 2 level of sensitivity, which is the current EDM limit. And first question is, which ones of these have enough sensitivity? Well, this is a pretty ridiculous number of molecules, especially polyatomic molecules, to get trapped. We're not going to think about those anymore. The next question is, which ones can we make right now? And radium hydroxide, this 3 is very enticing, but we just don't know enough to do an EDM experiment with radium hydroxide right now. It's never been produced. So we're not going to think about that in this talk. And that leaves these 3 candidates. And I want to explain why, even though this intrinsic sensitivity of SrOH is not as favorable, why we think that it's ready to do an EDM experiment in scare quotes tomorrow. That is not a literal tomorrow. But the other 2 on this list need a bit more work. And we're really interested in just pushing forward and seeing how this system behaves and trying to really optimize this number and probe new physics in SrOH. So just going down that list very briefly in terms of sensitivity, YBOH is a great molecule, but it just needs some more spectroscopy before we can fully trap it. So there are some lost channels. Of course, many vibrational states are populated. We need a bit more spectroscopy to figure out how to repump those. There's another kind of conceptually distinct lost channel, which is interesting, which is that the ground state of YBOH has a filled F shell and a single S electron on the ytterbium atom, but there are excitations of an F electron to the S shell, which can produce these metastable intermediate states between the ground and excited cycling states. And these can get populated over many photon scatters. The best place to learn about this actually in a paper from the Chung, Steinle, and Tarbit groups on YBF, which has this problem because it really just comes from the ytterbium atom. So we've measured one of these decays in YBOH. It shows up here at around the 10 to the minus 4 level. So that means if you scatter 10,000 photons, you'll get a decay to this state. And based on Lan Cheng's calculations, we expect there's about 3 of these states that are significantly populated. So this is an additional thing that we have to work out in addition to the normal vibrational states. We can certainly do it. It just takes time. So we can't start an EDM measurement right now on this molecule. BAOH, I'll go through a little bit more quickly. So we heard about how BAF has some challenges, but it is feasible to laser cool. But that doesn't generalize to BAOH because the delta state, which is below the A pi cycling state that offers the narrow line transition in BAF, actually has a bending mode which is nearly degenerate with the main cycling state. And the spectroscopy papers describe both A and B as severely perturbed. And when you read that, you do not want to laser cool it. So we have abundant evidence this is just not going to work, even if BAF works. Also, there's not much spectroscopy on it. This is just not a good choice. So SrOH is great. I showed this picture before. It has already been laser cooled in 1 dimension. The level structure is just what you expect. There's no intermediate states from the F holes or from a delta state. And we think we can just essentially go forward and trap this molecule. So in 2017, when that original laser cooling work was done, the expectation for what it would take to get a full trap of SrOH was shown here on the left. And this looks fantastic. You only need a few repumpers, and it's really not that much harder than a diatomic analog like SRF. This was the configuration used for the first SRF MOT. But what I want to stress here is that this extrapolation from what you know when you can scatter a couple of hundred photons just does not work because fundamentally different mechanisms kick in at the part per thousand or part per 10,000 level. And so you really just need to look what it actually takes. This is the same kind of picture in SrOH, except instead of an extrapolation on the left, it's the actual laser configuration used to generate the SrOH MOT compared to the first CAF MOT. And the lesson here is you just need to measure what states are populated. You should not try to measure part way and then think that the next few steps are going to follow the same pattern, because different mechanisms kick in. So we did that in SrOH, and the way we set this up is we optically cycle on either the A or the B state. Most of the time when we optically cycle, the ground state that we start in is populated. Sometimes another vibrational state is populated. And we do this in a cryogenic buffer gas source, which has SrOH molecules coming out. We excite, in this picture, out of and then back into the page. And the molecules fluoresce. We focus that fluorescence into our spectrometer, and the wavelengths are dispersed on a grating and imaged on a camera. So different wavelengths appear on different columns of pixels on this camera. And by looking at the intensity of light at different wavelengths, you can infer the intensity of decays to different vibrational transitions, which are typically many nanometers apart. So when we do this cycle on X000, which is the ground state, to A000, and it looks fantastic, but I already told you that you should not just look at this picture. You have to zoom in, and quite a few more states come in. So this middle number is a bending mode. When you have two sequential numbers, that means there's an excitation of the stretch and the bend at the same time. And the level that we care about is this 10,000 photon level. That's sort of the right scale, at least, for how many photon scatters you need to trap the molecules. And you actually need to measure below this level, because we see there's a few states down here which will add up to the 10,000 photon level. So if you just took the measurements down to a sensitivity of this level, you would leave out all of these states, and then you'd try to do your optical cycle, and you'd have significantly fewer photons scattered per molecule than you expected. So you need to go down to sensitivity where anything can add up to a level you care about. This actually looks pretty manageable. So we have a couple of excitations of the stretch, a few excitations of the bend, one combination band that we will care about. We can probably leave this one out. It's a factor of 3 or so below the level we care about. Then we compared to B, because maybe B is just better and we should go look and see if we want to cycle on it. And it's a lot worse. So this is essentially because B is higher up, and vibrational excitations in A can be close to the B state and induce these very weak mixings, which give intensity borrowing to high bending mode. So for example, this state, which is 5 excitations of the bend, we do not want to deal with. So we're not going to primarily cycle through B. We also did this up to B100 and A100 because we want to use those for repumping. And there's very little chance that those were going to give a major problem because they come in late in the cycle. But we just wanted to be sure we wouldn't get any crazy surprises. So this allows us to design a laser cooling scheme. It's shown here on the left. These arrow thicknesses are representative of the relative power requirements so that each state is approximately equally limiting in the scattering rate. And something I really want to stress here is almost all of these states have been studied at high resolution. SrOH is just incredibly well understood. We recently observed the B010 laser cooling state, which we want to use for repumping this combination band. We found the B200 manifold. We're working on the rotational assignment, but that's very easy compared to most of the spectroscopy we've heard about, so we're not worried about getting through that. And then the last spectroscopy we need to do is understand the 110 and 300 repumpers, which we're planning to do with the FM spectroscopy techniques that Nick described briefly. All the other lines are known, so we're not actually ready to start laser cooling this quite tomorrow, but this is a much better situation than a generic new molecule that you might look at. To implement this, we're using all SFGs. This is probably a little bit technical, so I can answer questions about this, but the idea is just to get high power fiber amplifiers, combine them, send them through an SFG crystal. The trick that we're playing to save a lot of money and complexity is you can put in multiple seeds combined into a fiber amplifier, and it amplifies all of the seeds that you give it. And then you pass it through a crystal, which is tuned in temperature to perform the SFG function just on one of the seed wavelengths. And then the rest just passes through, and you can do the other seed wavelength on another crystal. So you see down here, these are all very low power requirements because they come in late in the cycle. And so we will be able to save a lot of money there. I'm running a little low on time, so I just want to stress that we really care about high flux because we need high numbers. So we're trying a few tricks, including things that we heard from Tom on Thursday. And this was our EDM lab a few months ago. There's a problem here, which is that this isn't our EDM experiment. And the bigger problem is there's diatomic molecules being made in here, and we just don't want that at all. So the ACME experiment moved out of this lab, and we're moving in to set up the EDM experiment. And so we're building a new beam source, which, as you see, has no diatomic molecules being made in it, and we're really happy about that. All right, so this is the team, and take questions. Thanks.
Question. Actually, I had a question about the ultralight dark matter sensitivity. So how would using something like SrOH compare to using like something like CAF for actual sensitivity to?
If you can measure with the same absolute frequency sensitivity, say both experiments measure with 10 microhertz, then they're essentially the same. So the choice of platform is really, do you want to operate the experiment using a Raman transition over 10 terahertz, or do you want to operate it with microwaves? And my personal opinion is it's actually not that clear which one will win out because it comes down to systematics. You kind of just need to do the experiments and find out what limits each.
So are there molecules you can pick that would be more sensitive?
Not really. The harmonic scaling goes like the square root of proton to electron mass ratio. The anharmonic goes linearly in that. And so if you're just fixed to a given absolute sensitivity, you want this transition energy to be very large. But it depends what limits the experiment in practice.
Any other questions? If not, I guess we should